We're going to be talking about evolving your distributed cache when you're moving towards continuous delivery. And this talk is kind of set up in two sections. The first half of the talk is kind of a case study of how build evolved from the early days to the architecture we have today. We'll talk about some of the problems we had trying to scale up as we grew. And then the second half of the talk, I'm going to discuss the specific problems you'll have, things that you don't really think about until you actually run into them when you start implementing continuous delivery. So first, build. Build is a personalized online home improvement shopping experience. It's a mouthful. Basically, we sell toilets online and faucets, and it has grown from there. So pretty much any home improvement thing you can do, we will sell it to you. We do 91 million visits per year. We have 109 professional tradespeople. So that basically means we kind of target the contractors, designers. We have salespeople that are trained in specific, like flooring, and they basically kind of work with our clients on a regular basis. So if you're on our website, you see some face pop up, it actually is one of our salespeople, and they will help you out, and they have some training in what they're selling. Okay, so early days. Build started out as faucetdirect.com. Basically, it was just a single website. The site and the company grew really rapidly. Even the CEO was actually doing the coding. It wasn't great. Deployments were done at night, and of course, predictably, we started running into performance problems. So we're like, how are we going to fix this? Let's introduce some caching. So there were several distributed caching options out there, and we actually started with a Java-based caching, and again, predictably, we ran into garbage collection pauses, and that did not work out real well when you're trying to get your site to actually run. So we decided to use Redis because at the time it was what everybody else was starting to use. And it's hard to argue with the results. Redis can be clustered. It's blazingly fast, as everybody here probably knows already. Easy to maintain, and we're a Java shop primarily, and it had built-in support for Spring. So it was a natural choice for us. We don't do scale like a Google or an Amazon, but we do, like this little screenshot is from probably a couple of years ago, where we had 55 days of uptime in Redis and served almost 3 billion requests. So again, hard to argue with the results. It was way better than using the previous Java implementation that we were using. So it was really effective. So we kept adding more data to our cache. And we did our deployments at night. And we started realizing or running into errors when we deploy. With a new version of the software, something structurally would change with the thing we were caching, and we would have to end up flushing or purging the entire cache every time we did a deployment. So you can imagine this kind of sucked because we're doing it at night. And we basically continued to grow. We had multiple web storefronts. We put more and more data in the cache. The sites were always slow after deployment, so you can imagine if we're deploying at night, like 12, 1 o'clock in the morning, we would flush the cache, and then we would have to prime the cache prior to production coming on in the morning. So our sophisticated priming mechanism was get a bunch of people on the website and just click around pages, and that's how we did it for a while. I suspect other companies have kind of run into this as well. And you held your breath, and you hoped that by the time morning hit, that the site would stay up. So we needed to fix it. So just like everybody else, we're like, oh, this blue-green deployment seems pretty nice, so let's try that. So we basically decided, OK, we're going to have two identical environments. They'll talk to the same databases. One was always the active one, and then the other one was dark, meaning the site wasn't actually touching it. So what this allowed us to do is we could deploy in the day to the dark servers while production ran on the other environment, which was great. But we still had to purge and then prime the cache. And so again, it was working for a while. At least we weren't having to stay up till 4 or 5 in the morning, but it still wasn't great. So our production traffic continued to grow. We still needed 2 different Redis clusters. And we decided that we can't just have our developers just hitting the web pages. So what we ended up kind of coming with a hybrid approach. We called it internal canary. So In a blue-green environment, one side was always production. That's what the site was using. And all of our salespeople would be turned on to use the dark servers. So they were kind of like our natural primers for us. So that's what we ended up doing. And it worked. But we still wanted to share the cache. It was kind of a blocker for us going to continuous delivery. So we had to kind of solve that. So today's architecture. We are actually today still in a data center. Our data center is owned by our parent company. It's in the middle of the country. We have all of our traffic coming in through an edge gateway. And you can see we have stores, we have a mobile API that comes in, and all of this is flowing through what we call the platform API services. And that's kind of like where I spend most of my time. I'm a back-end engineer there. So all of the tools, the stores, the APIs, the public APIs all flow through this back-end service. So you can see that's kind of where we introduced the distributed caching. It sits between our internal APIs and all the databases. So common data access, common business logic, we can enforce security, and then of course caching. So we know that we're still in a data center. We know we're going to be going to the cloud at some point. So we started thinking about how are we going to kind of evolve our architecture to where we can get there. So if you haven't heard of it before, I'm a pretty strong believer in 12-factor applications. This is like a manifesto. If you haven't heard of it, you can go. There's a link to it by the folks at Heroku. And basically, there are 12 principles of being like a good cloud citizen within once you move to that environment. So load balancing, metrics, log aggregation, circuit breakers for third-party calls, and most importantly, rolling deployments. So even if you're in a data center today, and even if you have a big monolithic app like we do, you can still do continuous delivery and not be in the cloud. So we are actually using a tool called Harness. There are other tools that are similar. One's called Spinnaker. I'm sure people are familiar with Spinnaker. But basically, these tools kind of automate the continuous delivery side of your CI/CD pipeline. So why? You can push your code to production often. And it actually is counterintuitive, but the risk is smaller because you have less changes between your releases. So instead of having these massive releases every 6 months, you're basically just incrementally creating small changes. You're getting immediate user feedback. It is great once you get there. It is hard work to get here. And you really do need to use some sort of automated tool. So again, this tool here, Harness, is basically going to automate, we use rolling deployments. So we have 10 nodes in our API, and it will drop 2 out, install the new version. We'll monitor for 15 minutes. It's actually hooked in to our log aggregation, which is Sumo Logic, and our metrics, which is New Relic, but they hook into others. And it will use machine learning to detect differences between the new version and the other versions. And it will also automate the rollback if something goes wrong. So you'll see the last step there, it says manual. Don't let that fool you. We're still automating that when we get to production, but there's a gatekeeper there. And the reason we did that is we didn't have one initially. We just said, this is great, let's just go ahead and do it. It turned out, it pretty much, consistently, because we had a big monolithic app, there would always be something that would block the deployments. So my team would have to constantly babysit it. So we had one person each week in our sprint that was basically their job to watch the builds. And it really wasn't that effective. So we decided we're going to put a gatekeeper on this. We're going to deploy twice a day, which is still pretty fast. And it also means that we don't have to have a dedicated resource to babysit this the whole time. So obviously, if you're in a cloud environment or even in a data center, you can use other approaches. We had limited resources, so we use rolling deployments. If you have a cloud environment, you have the ability to spin up, other environments and start, sending the traffic to the instances. So with us, our rolling deployments, I'm sure everybody knows how this works. Going from top to bottom in time, you have an initial version of all your software. Again, your automated tool will install the nodes on 2, and then if nothing goes wrong, then it rolls forward and then rolls 2 more, and then eventually you'll get to your new version. So the interesting thing we ran into, trouble spots. When you have two versions of your application that are concurrently running in your environment and they're sharing the same cache, you will run into some really interesting errors. Like, and again, I'm going to get into this in the next part of the talk about kind of like some of the problems you run into and then how we ended up solving them. My examples are all in Java. However, the principles can be used in any tech stack. So, okay, so we call this our unified caching model, which basically is a fancy way of saying, hey, we can share Redis between two versions of the app, even when the structure of what you're caching changes. So, demo setup. So now I am going to switch back and forth, and let's hope the demo gods are on my side. Okay. First things first. The link to this is on every slide, so I'm just going to say right away, you don't need to like write it down madly. It'll be in plenty of my slides. So I have an example here. You can see I've got version 1 and version 2 of this application. I'll get into what they do. The unified cache is the library we've written for Spring that kind of customize how Spring's cache abstraction works. I have a Docker Compose file here that just it allows us to start up Redis in your local environment without having to have too much pain. I also have a collection, a Postman collection here, which makes it easy to call the examples. And if you really like reading walls and walls of text, I've got a gigantic README here. So pretty much everything I'm going to talk about here is in this GitHub repo on the README, and I am always open to talk about this stuff because it's cool. Okay, so. And I'll try to minimize, how many people are actually using Java? Okay, fair amount. I'm going to minimize the Java-specific spin on this as much as I can, but there's certain parts I'm just not going to be able to do. So, just want to go back to this, maybe. Okay, so like I said, Docker Compose, pretty simple, just create Redis. I'm actually not even connected to the internet, so hopefully this will work. So you can see I've got Docker running, and I've got Redis going. Okay. I am going to touch on this just briefly. There's a talk actually following this one. I think Mario Gray from Pivotal is coming to talk specifically about Spring's cache abstraction, Spring Boot. So I'm going to kind of skip over a lot of that stuff. Just know that in order to use caching, you have to have these two dependencies. And through the magic of Spring Boot, it will automatically configure your Redis caching for you, which is really nice. OK, so what we're going to do is we have a customer object here. It has just basic, customer information. This is the version 1 of the app, so you can see I'm in version 1. And then version 2 is just going to add an address object to it. So, the address obviously is going to have your normal fields you would expect to have an address. I just wanted to have two different versions, of the model. Okay. And then each data access object. So this is your classic data access service layer, controller. If you've, your layered architecture. I'm not actually hitting a database. You can see here, very sophisticated. We're just creating in-memory hash map inside our data access, and this is the version 1. And then version 2, I'm adding address information to it as well. Okay, now the interesting stuff. So for those that don't know how Spring's caching works, I have to kind of talk a little bit about this. You put an annotation around a method, and basically, based on the arguments coming into the method, it will cache the results for you. It does this by just kind of wrapping your method with a proxy. It's pretty cool. This here is just a string value that is, I guess I can go to it. Very exciting, customer by ID. And you can see I'm just grabbing the customer ID, the argument, so that's going to be my key, and then it's going to serialize the customer object. That's how Spring's going to work out of the box. You can see here I've added an artificial sleep of 5 seconds to just kind of exaggerate a slow call to our imaginary data access layer. And then one last point on the Spring stuff, and I'll get off of it. When you modify it, you can evict the same cache value. So inside, you can say I'm reaching into the customer object being passed in. I'm grabbing the customer ID, and I'm evicting it from our cache. So just know that Spring does a lot of that for you. It's really nice. And then I have the controller. Also kind of some Spring magic, but just know that we're creating an endpoint here that's going to be customers, and that I have a get mapping that takes the customer ID, and all that is really doing is going to the service layer and then hitting our DAO, which has sleep for 5 seconds. Okay, a lot of talking. So now I'm actually going to run both apps. So I have 1 and 2 going. Make sure they're up and running. Okay. I'm going to go over to Postman. Maybe. Okay. So I've got one version running on 8081. I've got the other one running on 8082. Let's see what happens. So I expect this to take 5 seconds. And we get our result. If I call it a second time, yay, our caching is working. We're getting it very quickly. Here's the first problem that we ran into at build when we did this. We got errors because the cached version was not compatible with the version that we were expecting from our application. So that is unfortunate. And so if we look in to what Redis looks like, maybe. Okay. Okay. Come on, demo gods. There we go. So this is just connecting to that, the thing running in Docker. If we look at what this thing is doing, you can see, oh, customer by ID. That looks familiar. That's from our code. And there's our customer ID of 2. And you can see that out of the box, Spring is just serializing this as binary data. So this is going to be similar to any other caching mechanism you might use using any other stack. There's going to be some way of serializing the data. So I'm going to go ahead and delete that. And we're going to go back to my slide a little bit. So what happened? Version 1 of the app, it basically hits the cache and gets a cache miss because there was nothing in there. It retrieves the customer data from the database. It puts it in the cache, so you can see inside we've got ID2 and then our serialized customer. And then version 1.1 comes along and says, hey, there's a customer that's under this ID. It grabs it, and that's when you hit your bad things. So that was one of our problems we ran into. So how do you fix it? Okay, so the other thing I have done with this repo is you will find there are tags in here, so you can actually evolve the application kind of similar to what I'm going to do here. So all I'm going to do now is I'm just going to switch to a different tag. We were on the basic caching, and I'm going to go to the second one called serializer validating cache. It's another mouthful. And I'm going to go ahead and stop both instances because I'm going to try that. Okay. Okay. Bookmarks. So what do we do here? We've now added, if we go back to our dependencies, instead of using the Spring's standard dependencies, we're now using this unified cache. So all the code for this that solves all these problems is actually in this repo. So if you want to really look at what we did underneath the covers, you can certainly do that. So that's really the only change we had to do there. And then we use the same mechanisms that Spring Boot does. So if you put that dependency on the class path, you will get this kind of alternate version of caching that solves this problem. So I'm going to go ahead and start these up again. Okay. And they're starting up. So here's what we did. Java has a concept of having a serialized UID. It's back to the old days of when you did standard serialization. You can create a UID, and every time you make a change to your model, you increment that thing. So we decided we were going to latch onto that same model, except that our serializer uses JSON instead of the normal. And we picked it partly because we already had JSON serialization as part of the Spring application. So what we end up doing is we end up serializing our objects as JSON, and we actually take the serialized UID and we encode it in with our messages. So it allows us to kind of verify, like a checksum almost, to make sure the structure that's stored in Redis matches the structure that we're expecting in code. So going back to Postman now. I'm going to go to application 1, and I expect this to take 5 seconds. If I do it a second time, that's fast. That's what we expect. Now over here, remember we got the error last time. We're now using that checksum, and it actually is going to take 5 seconds. And you can see that now we actually get our address information. That's cool. And now if we hit it a second time, it's fast. However, we come back here, guess what's going to happen? It's going to take 5 seconds because the checksum failed. So this is the second problem we ran into when we were doing this. Let's go back to the slides. Just to kind of summarize what we just saw. Version 1 cache miss, it retrieves the value from the database, it stores it in the cache. You can see ID 2 has got just the basic customer information. Version 1 comes along, it grabs it, but the checksum fails because the serialized UIDs are different. It then retrieves its version, and it puts it into the cache with the address information. So when version 1 comes along again, its checksum fails, and it has to reload it. So what ends up happening is we coined it cache thrashing. I don't know if that's a thing, but that's what we called it. Basically, if you have version 1 and then 1.1 and then version 0 going back and forth, you're never going to see the benefits of your caching. And this actually hit us. This is what it looks like in the wild. And so each of these, I'm not sure people can see that real well, but each one of those vertical bars is when we're deploying our applications into our production environment. So here's what happened. We deployed it, and Harness warned us immediately that this method was taking quite a bit longer than it normally does. You can see the throughput doesn't actually change at all. So we're like, turn it off, turn it off. So you can see we basically rolled it back and went back down to normal. So we debated on what to do. We're like, let's just try it again, maybe it'll work. So we did, and you can see the deployment, and then the same thing happened again. And this time we just left it in to kind of like triage what was going on. And that's when we started detecting like, oh, okay, I see what's going on. Both versions are kind of like, are stepping on each other. So finally we said, okay, roll it back. We came up with a game plan. We're like, we're going to roll this forward, and we're just going to let Harness continue to deploy, and we're just going to ignore the fact that this method's taking longer and just hope that it goes down afterwards. And that's exactly what happened. So you can see that each one of those green bars is when we're taking 2 nodes out of our server and then 2 more out of our server. So we're transitioning from one version to the other. Once all of the versions are the same again, it went back to normal. So that's cache thrashing. So how do you solve that one? Okay. Oh, one more thing I forgot to mention. Let's go look at what this looks like now in Redis. Okay. Just ignore for a second that it's a hash. We're going to get into that in a second. But you can see here with the value is now being stored as JSON. And sure enough, you can see the UID is being encoded. The % UID is kind of just an artificial thing that we ended up coming up with. Whatever mechanism you end up using, it's up to you, really. So, and I'm going to go ahead and delete this. Refresh. Okay. So we're going to evolve this one. We're going to evolve this repo one more time. Let me shut these both down again. Okay. All right, I'm going to now switch to the tip, master. This is going to be the fully realized version of our caching. I have to update this because we have another change. Okay, so here's how we solved it. If you had noticed when we were looking at that in Redis, the Redis client, we're actually storing the values in hashes. So you might be going, well, why did you do that? We did that for the following reasons. Bookmarks. Let's go here. Okay, so you'll see we actually have our build. I mean, this is pretty standard. If you have a continuous integration, you can inject a build number and increment it each time. So here's what we decided to do. We're like, what if we keep the same bucket for the customer ID, and instead we hash by the version number, so each application build can have its own copy of the same cached value. So basically, that's what we did. So you can see version 1 is here, and for the sake of this demo, it's just we manually update it. Obviously, you're going to want your tools to automate this, so you're not touching this build number. So there are some things you need to do to make this work, like through your tooling. And so the second application, you can see we just have 1001 and we have 1002. All right, let's fire this back up now. Running, okay. Going back to Postman. All right, that's going to take 5 seconds. And if we hit it again, yay, it's fast. If we go to the second app, it'll take 5 seconds. And it's fast. If we go back to version 1 now, it's fast. So let's look what it looks like now in Redis. Okay, refresh. You can see we actually have 2 versions now. We have version 1001, that's basically storing the customer like that. And then we have the second one that's storing it with the address information. So that's actually how this is working. So the cache abstraction is looking from the key, grabbing the application version that it needs, and will then grab the right version of the customer object. One more trick I want to do. See if people could guess. If I stop version 2, application 2, and I increment the version once, and I start this back up, are there any guesses of what's going to happen the first time I call the app now? So if I go to 2, will it take 5 seconds or will it not? And we're going to try it. It doesn't. So this was the last trick in our playbook. Because we know that the previous version of the application has a serialized version, if we get a cache miss and it's not there, we'll find the previous version's copy, and we'll try to deserialize it. And if it serializes without having any checks and failures, we'll promote it. We'll promote it to that application version. So what that ends up looking like in Redis, you'll see now we have 3 values in there. And what happened is 1003 is basically using the same one that was in 1002 because the structure of the object actually did not change. So we'll go back to the slide deck. So we're just talking about the buckets. So version 1 came along, it got a cache miss, it retrieves it, it puts it in the in Redis. Version 1.1 comes along, it gets a cache miss because its version is empty. I actually have a check for promotion there. It actually does try to get the previous version. Fails because the structure has changed. It retrieves its copy from the database and it puts it out in Redis. And this is what it ends up looking like. So the customer ID, is the top level key, and then version 1 and 1.1 are actually stored and they have their own copy. Cache promotion, that's kind of like how this works. Very similar. Version 1.1 comes along, it has a cache miss, it grabs version 1.0's version. Again, let's assume that the structure is the same. It is able to serialize it without any checks and failures. It goes ahead and just does a cache put into Redis, and we never hit our database. So that's that last thing that we just saw. So to summarize, first of all, we used serialization checksums, and it's not completely obvious at first. You can't do it just at the top level. Like if your customer has a checksum, but your address structure changes, you need to be able to detect changes to nested objects. So it's really important for you to make sure that the serialization stuff is done consistently with your parent level and your child. You can't use that top level thing as a key in your cache. Use your build number as your nested hash key. Again, we tried all kinds of different mechanisms like using GUIDs and stuff like that, but when you have a cluster of n number of boxes, the most consistent thing we had was our build number, so we ended up doing that. And then finally, if you get a cache miss, go out and grab the previous version's copy and see if you can use it, because 90% of the time it's totally doable. So we actually ended up adding metrics around this to see exactly how often we were getting promotions and gets and whatnot. Okay, final notes. What about cache eviction? We were just talking about that. What if you have all these copies? What's going to happen there if version 1.1 says I'm saving something new about the customer? Well, the evict is happening at the top level key, the customer ID. So it evicts all copies. So we kind of got that for free, which was kind of nice. We were also worried because we have multiple copies of the same object, like what's this going to do for resource allocations? We kind of manage this with time to live. Like we use a 1 day by default, but in places where it's more critical, we just dial that down to even more. It really hasn't been an issue for us in our environment. Again, we're not at a Google scale, but we're not small necessarily. We've actually written this twice. We originally wrote it in Spring Boot 1.5, and again, this is more of the Java piece of this. And we actually extended the Spring default implementation for Redis and added these features. And then when we moved to 2.0, they basically told us, no, you just want to rewrite your own. So we ended up doing that. So what you will see in this example is really close to what Build uses today. The last thing is, if there's enough interest, we would consider open sourcing it. And again, you can always hit me up for any type of questions you might have. So that's it. Questions?
You mentioned in the second demo that it corrected itself after time. Is that right?
Second demo.
So the second demo you did, each version took 5 seconds when
Yes.
you alternated.
Yep.
But then you said over time it worked itself out or something like that?
So in the wild, when you have 2 versions at the same time, you experience that cache thrashing. So it works itself out. You basically have to trust your instincts and let it roll forward and ignore the fact that it's taking longer than normal, because once it finishes deploying and it's all in the next version, that drops off again and it normalizes itself again. So
Okay.
yeah, it was a tricky problem to kind of like triage at first. Yep. Anybody else?
When you went from the non-hash implementation to the hashed one,
Yep.
so on day 1, the first build or the build that existed wouldn't have had the hash. So what did you have to do?
It was no different than what we were doing. That like it was no different from the previous versions, right? We were having to purge the entire cache. So when the first time we had a hash, it was just really slow because it had to prime that hash value. Yeah.
Okay, one more question.
Yeah.
You said when a build does not have a version, it creates a copy of the previous version, right?
Yep.
Instead, you could have just bounced the previous versions, like the build 102 to 103, and then avoided a copy.
Yep. So what we are trying to do is we're trying to minimize the amount of times we have to make calls to Redis in our caching layer, because we were just concerned that if you have to keep switching back to previous versions and then calling Git rather than promoting it, we just landed on let's have each application have their own copy, and it worked well enough, so we just stopped. If we'd had like resource contention problems or we're blowing the memory, then we probably would have explored changing that. So the other thing is, if we do open source this, these are options that we would love to have some community feedback. This is not perfect by any means. It works for our environment though. Okay, anybody else? Okay,
Actually, I have a question.
Sure.
So you had an example of just showing customer data, and then you have keys that are build numbers.
Yep.
Are you using the same strategy for caching for any other type of data?
Any type of data, yep.
Okay.
So, whatever your natural business key is going to be for your cache, that's going to be your root key. And then we always use the application version to store that copy underneath. So when you add our library to your Spring application, you get that behavior for all caches.
Got it.
So
So for each application, like, are you spinning up a separate Redis instance for those type of data sets, or are you?
one shared Redis cluster for everything.
Got it.
Yep.
Okay.
Yep.
Awesome.
Yeah.
What was the hardest part of all of this in terms of diagnostics and problem solution?
The hardest part was solving our I don't want to stay up till the butt crack of dawn, priming our application and trying to solve that serialization problem. So that was a tricky problem because initially we were just trying to have the checksum at the top level, and we still ran into issues because the nested object would change on us. So solving that problem, with the serializer involved us getting kind of deep into the bowels of the Spring JSON serializer, pulling out serialized UIDs off of from Java class and concatenating those into the serializer. And then the other way around, when you pull it out, throwing an exception when those UIDs don't match. Yeah, it was tricky. That was probably the hardest part. Okay. Anybody else? Okay, 7 minutes left. Thank you very much.
Thank you.